Hi, welcome back. All right, so today we're going to look at heuristic functions. So at the end of the class, we should be able to devise a useful heuristic function for a problem, demonstrate how best first and A search, star search will work on a graph, and predict the space and time requirements for best first and A star search. Okay, so the idea is that if you think about what happens in both breadth first, depth first, and best first searches, you find that they sort of seem really strange when you think about them, what they do with goals. They just wander around until they find a goal and they say, I found a goal, and then stop. So what we're going to do is we're going to take into account the fact that we don't ignore the goals when selecting the paths. We're going to take the goal into account when we're going to select the path. So often we're going to use extra knowledge that can be used to guide the search. We're going to call these heuristics. So we're going to use the term heuristics as any extra knowledge that we're going to use. In particular, we're going to use a heuristic function. H of n is a non-negative estimate of the cost of the shortest path from node n to a goal node. So we're estimating how if I'm at node n, how close am I to the goal? So that's what we're going to use as an estimate. So H of n needs to be efficient to compute. We need somehow to compute it efficiently, or maybe we could even write them in a table and look up a table. So H of n, we can extend it to paths. So H of n1 to nk is just H of the last one. So let's assume we're going to go from n0 to nk, and then we're going to go to a goal. So it's the length from nk to a goal. So H of n is an underestimate if there's no path from n to the goal with a cost less than H of n. So it's an underestimate means that there isn't a shorter cost. So it's an estimate of the cost for the shortest path. So it's less than that. An admissible heuristic is a heuristic that's an underestimate of the actual cost of a path from a goal. So it's less than or equal to the actual path of a goal. Okay, so here's some example heuristic functions. If the nodes are points on a Euclidean plane, and the distance is the cost, then you can work, no matter how you walk through or travel through a Euclidean plane, the shortest distance is a straight line. So one heuristic function is just a straight line distance from n to the closest goal. So that's going to be an underestimate of any algorithm that's going to not necessarily take the shortest route. If the nodes are location and the cost is time, well, the maximum we can do the cost is time, well, we can look at our maximum speed, use the maximum speed. So the distance is the goal divided by the maximum speed, because that's the least time you would take. If the goal is to collect all the coins and not run out of fuel, well, maybe the cost is an estimate how many times it would take to return to to collect the rest of the coins, refuel when necessary, and return to the goal position. That's what we're trying to guess. And maybe you could just ignore walls or other things and ignore lots of parts of it. So in general, what we do is we're going to find it by solving a simpler problem, a less constrained version of the problem. So we're going to find heuristic functions by doing that, and we'll get some practice solving heuristic functions. So the obvious solution is to what's called best first search, is to select the path whose end is closest to the goal according to the heuristic function. So what we're going to do is we're going to select the path on the frontier with minimal h value. So that's what we're going to do in best first search. It's the obvious solution. And is to treat the frontier as just a priority queue ordered by h. So it's just the generic search algorithm, but we're selecting the node that's ordered by h. And this seems like a good idea. However, here is sort of an example of what happens in here. So if S is our start node, and we're using Euclidean distance, then the best route is to go via this left green and down to this. However, best first search will not do that. Best first search will go to S to this first red node, and this looks better, this looks good, this looks good, this looks good, this looks good, and it goes around and around in a circle and never gets to G. So essentially, the heuristic here is misleading us. So you end up with this loop around here, and this loop gets longer and longer, but best first search doesn't take that into consideration. It just starts here and just keeps wandering around because they're all closer to the goal than the other elements of the frontier, which are this one and this node. So it'll never actually find a solution to the goal. So while it looks like a good idea, it's not a very good idea. So what's the problem with this is that this node here can't be the best node, because if you keep going around and around here, you keep increasing the cost of the node. So what we're going to do is we're going to take into account the cost of the path, and the heuristic function is going to give us something better. Okay, so what we're going to do is we're going to use, I skipped over something, don't worry about it, we'll talk about that in class. So we're going to use A star search, uses both path cost and heuristic values. So A star is going to take into account both the path cost and the heuristic value. So we're going to use the cost of P as the cost of path P, and H of P is the estimate of the cost from the end of P to a goal. And so we're going to use F of P as the cost of P plus H of P. So F of P estimates the total path cost of going from a start node to a goal via P. So you're going to start, go from the path P to node N, and then we're going to go from N to a goal. And that's what we're going to use as our estimate. So this is our estimate of basically getting from a start to the goal via P. So the distance of this is the cost of P, is the cost of this, and H of P is the rest. All of that's called F of P. So we're going to now order it by F of P. Okay, and this is sort of a mix of lowest cost first and best first search, and it works out that it's actually better than both of them. So it treats the priority queue, treats the frontier as a priority queue ordered by F of P, and always selects the node on the frontier with the lowest estimated distance from the start to a goal node constrained to go via that node. So it's always trying to look at the total path length when trying to choose which path to expand first. So let's now ask some questions. We're going to ask these questions for all of them. Does A star search guarantee to find the shortest path or the path with fewest arcs? Or neither? What happens on infinite graphs or on graphs with cycles if there is a solution? What's the timing complexity as a function of the length of the path selected? What's the space complexity as a function of the length of the path selected? And how does the goal affect the search? And we looked at the other ones when we looked at, the ones we did last time, when we looked at breadth first, depth first, and best first. The goal didn't affect the search at all, but here the goal is affecting the search because we're trying to use that as part of our estimate. All right. So here's an argument that says if there is a solution, A star always finds an optimal solution and it's the first path to a goal selected. And there's a few conditions here. The branching factor is finite. So the branching factor of a node is the number of neighbors that the node has. So there can't be just infinitely many neighbors of a node. So as long as it's finite, that's okay. The arc costs have to be bounded above zero. So there's some epsilon such that all of the arc costs are greater than epsilon. If anyone wants to look up the problem of the tortoise and the hare, which is a classic problem, you'll end up knowing why we need costs bounded above zero, because there can be an infinite sum with a finite cost. There can be infinitely many values. The infinite path can still have a finite cost. And H of N's got to be a non-negative underestimate of the cost of the shortest path from N to a goal node. And that's all we need to show that it's admissible. So let's try and argue that it's admissible. Suppose we have a path to a goal is selected for a frontier. The question is, can there be a shorter path to a goal? So we found P. That's our one we found. The question is, can there be a shorter path to the goal? So there might be the idea is you might think, well, maybe there's another element on the frontier that will lead to a shorter path. So let's show that cannot happen. So suppose there is another path on the frontier, P prime, and we want to know, well, is it possible that P prime actually leads to a shorter path to the goal than P? Well, we know that P was chosen before P, and we know that H of P is zero because P is a path to a goal, so the heuristic function has to be zero. So because of this, the cost of P is less than the cost of P prime plus H of P. Right, so because of this, we know that because it was chosen before, this has to have we chose the one with the shortest cost plus H, so that this must be less than that because it was chosen in our priority queue. Now, we know that H is an underestimate, And so now we want to think about any path P prime to a goal that extends P. So if we do this, we'll find that the cost of P plus the cost of H of P prime, so the cost of P prime plus the H of P prime is less than or equal to cost of P double prime, where P double prime is a path to a goal. And this is because H is an underestimate, so that's the definition of underestimate. So if we pick these two together, we'll find that cost of P is less than the cost of P prime plus H of P, which in turn is less than the cost of P prime. So the cost of P must be less than or equal to the cost of P double prime for any other paths to a goal. Okay, so once we've found a path to a goal, there can't be a shorter path that can be extended from an element of the frontier. All right, so now the question is, well, maybe it won't find a solution. All right, so let's argue that it will. So A star can always find a solution if there is one. So we're going to argue, now we've argued if it finds a solution, it must be the shortest path. And then we're going to argue that it can always find a solution if there is one. So the frontier always contains the initial path of a path to a goal before that goal is selected. So the only time, so it contains the initial paths of all of the paths to the goals. So A star must halt as the cost of the paths on the frontier keeps increasing. So if we were adding a non-negative number to the cost, and so that must also increasing. And the cost will eventually exceed any finite number. So no matter what the cost of the goal is, the costs on the path will eventually exceed that. And that's all we need to show this. Okay? So now let's a question of so we'll talk about this in class. Suppose C is the cost of an optimal solution. So what happens to a path P where the cost of P plus H of P is less than C? What happens to those paths? What happens to the paths where it equals C? And what happens to the paths that exceed C? So think about that, and then we're going to ask the question, how can a better heuristic function help? Okay, we're going to talk all about this on Thursday. Bye.